So again, today we're going to be talking about basic introduction to computers and how they function. Um, for those of you who are of a younger generation, computers actually aren't that old. Okay, they're at least what we think of as computers aren't that old. And really, the first modern cell phone, I think, the iPhone was really the kind of inception of the modern cell phone, at least the smartphone as we think about it. And that was in '06, I believe. Facebook started in '04, which for some of you, we're getting close to your birth year. So, for you, it's been here your entire life for the most part. But for some of us, as we come from the '90s era, they're actually fairly new. And for some of you all, the save icon in Word just looks like the save icon. It's actually something called a floppy disk. It was a physical disk like a USB drive. It only held like equivalent to one Word document worth of storage, but it was a real thing back in, as they say, back in the day. So we'll talk about what those components of a computer are. I'm not going to go into the history because history is history, but we will talk about some of those underlying components. Again, for those of you who have joined, your camera must be on the entire time and your face visible if you want to be marked as present. If your face disappears, you will be marked as absent. All right. All right, let's talk about the computers. So there are several components to modern day computers. And if you actually get into building your own computer, you will buy some of these components. And nowadays, the DVD drive, the CD drive, we don't use that as often anymore. Actually, my laptops and my desktop do not have CD drives, and I have not missed it. All right. So we have the CPU, or the central processing unit. We have memory, we have a power supply, hard drive or SSD, and we have the video card. The video card is responsible for generating our graphics. So for any of you who game, whether it be on a game system like a PS4 or 5, if you can find one, an Xbox One, Xbox S, or if you do it on your computer, your graphics card is responsible for generating those images that you see on the screen, getting you 4K, or 1080p high definition. So the CPU, or the central processing unit, that's pretty much the brains of the computer. It does all of your number crunching. It takes the machine language and converts those into executable instructions. And then from there, everything that we see on the screen is what we have, is generated by the CPU and then translated by the GPU and so on and so forth. But the CPU is really responsible for doing everything that we want to do in a computer. The fact that I can have 4 different programs running right now is attributed to our CPUs and our modern CPUs, right? Something called multiprocessing, which previously you could only run one program at a time. Now we can run multiple programs because they're becoming more and more efficient at running multiple processes and multiprocessing. And we also have multi-threading as well, which is a different concept, but very similar in the same vein. There used to be something called Moore's Law, which said that every 2 years, the speed of processors would double. Or was it every 5 years? One of the two. Well, I'm sorry, not necessarily the speed, but the number of transistors on a processor would double. Transistors are basically little itty bitty, an analogy of them would be light bulbs on a CPU, ones and zeros. So how many ones and zeros could it process at one time was dependent on the physical number of transistors on the processor. And every 2 years, the number of transistors was doubling. However, now we're starting to reach just physical constraints. right? They're getting so small, they're microscopic, but they're getting so small, it's becoming harder and harder to double the number. So now instead of trying to double the number of transistors, what they're trying to do is make the multi-processing of our CPUs more efficient, adding more cores onto our CPU, right? So now when you hear quad core, can anybody assume what quad core means? How many cores there are?
4.
There are 4 cores, right? And then we have 8 core, 12 core, 24 core. And we're starting to get into the servers when we talk about that many cores. All right, so computers will then have a heat sink and a fan because if your components get really hot, they stop working. So if anybody can remember way back to the Xbox 360, if you heard of the red ring of death, that was your components overheating and melting, right? So the cooling wasn't very good on the Xbox 360. So it's important to have good cooling in your computers, even your laptops. When you start hearing that buzzing sound, that's your fans turning on, right? Your fans turning on, trying to cool those components, because whatever you're doing is running them hot, right? Sometimes it's just opening a Word document, depending on your computer, might buzz up the computer, right? And what you see here is we have the heat sink, which transfers the heat from the physical CPU and gives it a greater surface area for the fan to then disperse. So the heat sinks are really good for dispersing that heat. It's kind of like a radiator in your car, radiator and fan, same concept. If anybody has any questions as I'm doing this, please ask. And yes, today starts the first day of note taking. So make sure you're taking your notes. If you miss today, obviously you'll have to make it up somewhere else. Just make sure you get within that range. It's going to be around 20 to get an A. All right, so let's talk about memory. All right. And this kind of gets into why computers and laptops typically only last 2 to 3 years before they start running real slow. You know, you're talking about, come on, old one. I'm just trying to open Google Chrome, and your computer is moving at definitely not light speed, like a snail's pace. Well, that's typically due to your amount of memory in your computer. Google Chrome is actually a memory hungry program. And so, depending on how much memory your computer has, it could hog up all that memory and slow everything else down. So when it comes to memory and storage, they all kind of lump together and kind of do the same things. So your fastest and most expensive memory is your register, right? And this exists on your physical CPU. Then you have cache, which can be shared, and the register is on each individual core in your CPU. Your cache then is on the CPU itself and can be shared amongst your different cores. It's your next fastest and next expensive, right? Then we have RAM, or random access memory, and that's separated into physical and virtual. Your virtual RAM is kind of organized and controlled by your operating system. Your physical RAM is what you actually put into your computer. Nowadays, anything less than 8 gigs of RAM, as you progress about a year from now, is going to start slowing down, right? And 8 gigs of RAM as a programmer is really optimal because you'll be using a lot of RAM in your programs. Okay. And then we have our storage devices, so our hard drives, our solid state drives, and then we have our input sources, so our mouse, keyboards, cameras, mics, you know, all that good stuff. When you run a program, what happens is your program, all of the data for that program, let's take Microsoft Word, for example. Microsoft Word is all the data from it is stored in either a hard drive or your solid state drive, right? All the data for it. When you click run, what's happening is it's transferring all of that data, or attempting to as much as it can, into your RAM, your random access memory. That way it runs faster. If everything was in your hard drive, Word would be running incredibly slow. Because RAM is faster than your hard drive, it takes that data, puts it into RAM. Depending on what specifically you're using in Word, it might get transferred into your cache to speed it up as well. Right? Things that you're using most often, specifically what data is being used most often, it'll get stored into your cache. So we have these different layers of memory to speed up your execution of your computer. So for example, when you open Word the first time, it might be really slow booting up. That's because it's transferring that data into your RAM. If you close Word and try and reopen it, typically it'll be faster that next time because you already have data stored in RAM. Okay. Any questions so far? All right. And these first couple ones are probably the most or least interactive ones, just because we're learning about what a computer is. As we start programming, which will be in about 2 weeks, hopefully there'll be more dialogue between me and you, because we'll actually be learning how to control a computer. So I talked about cache, second fastest memory. The cache also holds your CPU instructions. So the CPU works off specific instructions. Move data here, multiply this, add these 2 pieces of memory. Very simple instructions. But from that instruction set comes everything that we see on a modern day computer. It's actually pretty incredible how it can be a very simple set of instructions can translate into everything that we see and able to do on a computer, right? Then we have RAM, or random access memory, stores all of your running programs or user programs, and it increases the access time, right? So the faster your RAM, typically the faster your computer will run in terms of your programs. So if you think about gaming systems, they'll have RAM that's shared between the GPU and the CPU. And that RAM is actually really, really fast RAM because it's shared. And because it's that game console, if you take it for more than just, oh, I'm going to play a video game on it, and actually take it for the hardware that it is, it's actually a pretty powerful machine. For those of you who are interested in crypto, it could technically be used as a mining rig because the GPU is so powerful. So let's continue. All right, so you have your hard drives and your solid state drives. And I'm going to kind of explain the difference between the two. I have a whiteboard that I'm going to try to connect now. I got to allow screen sharing. All right. All right, can you all see that? Yeah. Okay.
Yeah.
So a hard drive, HDD, right? A hard drive is actually a physical component with a little reading arm on it, reading and writing arm. It's literally a miniaturized record player. The only difference is you can read and write from it, whereas a record player, you typically only read from it. It spins a disk. So this disk right here spins, right, around a central point, and the little arm either writes to it using a laser, or it reads from it using a little, reading arm. And so hard drives are constrained by the physical speed of that disk right there, right? And physically, those disks can only spin so fast. And this arm can only read so fast. So they're constrained. So when you click on something, if you have a hard drive in your laptop or computer and you start hearing something spinning, sounds like something is starting to spin, it's probably your hard drive. Okay. Whereas a solid state drive is kind of the newer technology, although it is more expensive, which is why it's not as popular. It's becoming more popular now, but a solid state drive is what it sounds like. It's solid. There are no spinning or moving components. All it is little flash modules. So flash modules, it's like a USB drive, a flash drive. Right? We call it a flash drive. A SSD is basically multiple flash drives on one device. And then they all connect to a little controller. And I'm going to try to draw these little lines. Right? That controller just controls where data is stored on this SSD. You know, it's controlling the logic for multiple flash drives. There are no spinning components. There are no moving components. So in that sense, it is a lot faster than a hard drive because it's not constrained by just physical constraints, right? However fast electricity can move around this SSD is the constraints. And as we know, electricity moves at almost the speed of light. Okay, almost. And SSDs, obviously, they're getting faster and faster. And, you know, one of the trade-offs is the cost. Same with, you might ask, why don't we just fill our whole computer with RAM? Just throw out hard drives, throw out SSDs. Can anybody kind of tell me why we wouldn't want to do that? Just use all RAM?
Because RAM is volatile. So when the peak state turns off, we will lose everything.
That is true. Actually, I wasn't even thinking about that, but that's true. That is why we wouldn't want to use RAM. So RAM is volatile, meaning once you turn off the power, all of the data that's in RAM is lost. It loses everything, right? Hard drives and SSDs are non-volatile, meaning when you turn off the computer, hopefully, if you didn't do something wrong, all of your data is still there. Another reason why we wouldn't want to use RAM is just it would be so expensive. So 16 gigs of RAM, I think, is about $100. 1 terabyte of hard drive is about $100, right? So there's the trade-off. You can get a lot more storage from a hard drive, although a lot slower than RAM, right? So if I'm storing a whole bunch of videos, for example, this video right now, or all of our lovely PowerPoints, right? I put those on a flash drive. They're cheap. I don't need speed for those, right? However, if I'm running, I do research in cybersecurity and I do artificial intelligence. If I'm running one of my models, I need speed. So I have 32 gigs of RAM in my computer because I need all of those gigs. I use about 20 to 25 gigs each experiment. And I need the speed that RAM gives me. So that's why you wouldn't use RAM for your full computer setup. All right. And again, if you all have any questions or even comments, please stop me. I don't like monologuing. All right, so then we have our power supplies, basically the heart of the computer. They're responsible for converting AC or alternating current, which is what is in our walls, to direct current that is used in electronics. Out of curiosity, can anybody tell me why we use AC for wall power? This is just a curious question. It's not part of this class. See if there's any electrical engineers out there.
Isn't the like direct current too like strong?
Say that one more time.
Isn't like the direct current like high in voltage or something like that?
It just depends. They both can be high in voltage. So direct current is used in pretty much all electronics, right? It goes from point A to point B. Electricity goes into this little ring light that I'm using and out the other end. Well, the only problem with that is, right, we use electricity. It comes from a electrical source, which is usually a power generation station or power station, all the way to our homes, our campus, wherever it may be. Travels a long distance. Direct current has loss. So to keep it more reliable, they use AC power to go from the stations to your homes. AC alternates back and forth, keeps it a little bit more level, and then we convert it to DC at our homes. That's the only difference. Anyway, continue. So then we have GPUs, right? And if anybody was interested in buying a GPU recently due to crypto mining and gaming, they have become incredibly expensive. But GPUs are good for video output. So if you're doing video editing, you need a good GPU. If you're doing scientific research, for example, my artificial intelligence models require a strong GPU to train. Or if you're doing gaming, if you want to get those top graphics, textures, and whatnot, a strong GPU is required. All right. So the GPU is responsible for basically doing fuzzy number crunching, right? A lot of numbers at the same time. They're really good for that. Our motherboard holds all of our components, right? And this is what you would find in a desktop. So anybody interested in building their own computer, these are all the components you would need. So the motherboard, all of your RAM would go here. These are RAM slots. Your CPU goes here. Your GPU would go over here. Your hard drive would connect over here through SATA. Right. Your power supply connects right here and right here. All your I/O is over here. So your USB connectors, your Ethernet connector, maybe you have a Wi-Fi card, they all go over here. So our motherboard really just holds all the components and they communicate over our buses. Don't ask me what that acronym stands for. There are far too many acronyms in tech. Just know it's a bus. And there are little tracks on this motherboard. You can't see there because this picture quality is trash. But there are little tracks on this motherboard that the data traverses. We have our communication devices. And I believe we are getting towards, well, we're towards the middle. We'll talk about programming in a second. Oops. Didn't mean to do that. All right. We have communication devices. So our network interface card, anytime you connect to the internet or a network, you have a network interface card. Okay. And so the network interface card is responsible for all your communication. And each card has a physical address called a MAC address. And then if you are connecting to the internet, you'll have something called an IP address as well, which we'll talk about, I believe, next time, what the difference is and how IP addresses are determined. But every network connection has a corresponding network interface card. So for example, your cell phones have several network interface cards. Right? One is for Wi-Fi. One is for Bluetooth. Another one is for NIC, which is, or NFC, near field communication, which is what you use for Apple Pay or Samsung Pay or Google Pay or whoever's Pay. Right? You use NFC. For a desktop or maybe a laptop, you might have another one for Ethernet. Each one of those are individual network interface cards that have their own unique MAC address. And if they're connected to the internet, such as your Wi-Fi card or your Ethernet card, they'll have IP addresses as well. All right. All right, computer programs, right? Otherwise known as software. It's how we control how we control computers, right? And they're written in different programming languages. And, you know, anytime you use anything on a computer, it was written by somebody. So my philosophy is, yeah, everything that we use is great, but why can't you write something better? Right. And if you have the skill set to write code, you can. Right? Literally, if it's open source, which means the code is out there, you can look at the code and say, this is straight trash. I can do this better. Right. And so as a programmer, you have the ability to write whatever you want, make a computer do whatever you want. If you want to get into game design, download Unreal Engine and start programming. If you want to get into scientific research, start learning Python. And you want to get into artificial intelligence, self-driving cars, learn Python, right? If you want to get into building websites, learn HTML and CSS and JavaScript. If you want to do X, Y, and Z with a computer, learn the language, write the program. You literally will have the ability to, you could potentially be the next, Mark Zuckerberg or who else has invented? Bill Gates, right? They were programmers. It's just learning how to code and then putting it, together. So here are the different languages that are at play from a computer. So we have our hardware and our machine language, right? Machine language, trust me, don't try to learn that. It's just not, it's illegible. It's for machines, right? You're like the Matrix, if anybody remembers the Matrix. Assembly language ain't much better, but people actually, and I know there's a typo on this slide. Wait, actually, is there? Yeah, language is definitely spelled wrong right here, but I didn't make this picture, so don't judge me. So assembly language, again, is not much better, but people used to program in assembly language, but thank God we don't do that anymore. We have higher level languages like Java, for example. You see C right here. Now we're even above C, we're on Java. C++ was the next step. The next step above C++ was Java. Java, when you write Java, it's so much easier to understand than assembly language. I think I have an example of that. So here's assembly language. Here's machine language. If you all can understand that, please teach me, because at this level, you literally control the memory in a computer, like down to its most granular form. Yeah, I don't know none of that. But if you know it, if you are willing to learn it, by all means, you could make a lot of money. All right, so what was the problem with assembly language? It required important knowledge about specific computers. You had to know what type of processor was in the computer, what type of RAM. And I mean, when I say type, not only the speed and whatnot, but also the manufacturer and what kind of standard they have. When you have that level of control, you can make catastrophic errors and completely break a computer. It's hardware specific, and it's no longer popular because it just was very difficult to learn, and it was very easy to make a mistake. Our higher level languages are more English-like, right? They're easier to learn, and some common examples of that are Java, C++, and Python. Java and Python are actually my strongest suits, but I do a lot of programming in C++ because I'm programming Bitcoin. Bitcoin is written in C++, and I'm modifying the source code of that. Java, I use a lot in my research, same with Python. So depending on your use case and what you're trying to do, you may have to learn different languages. Here's an example of a high-level language, Java specifically. Radius equals 20. Well, that's easy to understand. I have some variable radius and it equals 20. So if I were to ask you what's the value of radius, hopefully you would answer 20. I'm trying to compute the area. Area equals, everybody knows how to compute the area of a circle, right? Pi r squared. That's terrible. I know you all didn't know that answer. That is absolutely terrible. The radius of a circle, the area of a circle is pi r squared. Which leads me to my next question, what is the perimeter of a circle? That's absolutely terrible. If y'all have to Google this, it's bad. I feel
Isn't
sorry
it-
for y'all generation. Anybody know what the perimeter of a circle is?
Isn't it what's it called? Diameter times pi.
Yeah. It is diameter. Yeah, that's right. That's right. I ain't gonna say that's wrong. It's 2 pi r, which is diameter times pi. Thank you. You just saved your whole generation. All right, anyway, we say area equals pi r squared. So r times pi. That's very simple. A lot easier than whatever this crap was. This could be like doing the area of a circle, but I have no idea what it's doing. Versus this, I can assume what this is doing. If we all know our equations from geometry, we know what this is doing. If I want to display these results to the console, right, which we'll learn about later, system.out.println, println. Well, I guess we're printing something, right, to the system, and we're going to print the stuff inside these parentheses. Okay, a little bit easier to read. And of course, as we go through this class, one of our first programs will be to print to the console. So you'll know what this means later on. All right, so everything is described much closer to the application domain, which they are used. For example, radius. I have the radius of a circle. I can name a variable radius. And these instructions are then translated by the compiler, right? Which again, we'll learn about the JVM and the compiler and all that stuff later. But we have an intermediary that's responsible for translating what we write into machine executable code. This results in much higher productivity. Now, all I'm trying to do is calculate the area of a circle. That's it. I don't want to have to write 1,000 lines to do the area of a circle. Now it's literally one line. Area equals radius times 3.14159. And then there's some more after that. And there's a lower risk for errors. You can't modify the actual memory of your computer, which could break your computer. So when we compile, basically that just means we're converting what we write, our source code, into executable code for the machine. That's what compiling is. And we have a compiler that's responsible for that. Right? So when I tell you later on to compile your program, all you're doing is clicking a button and it converts it from source code to executable code. Any questions? All right, if there's no questions, I guess I'll give back to you 12 minutes. With that, I will see you on Friday. We have lab 2 on Friday, and I don't believe, or lab 1 on Friday. I don't believe there's an assignment, so no assignment this weekend, just lab 1 on Friday, and hopefully that shouldn't take you too long. All right, I'll see you all on Friday then.
Courtesy, Friday.